Hello again. Now we have all those tests together. We're going to think about the strategy for testing series. We should always remember the test for divergence when the limit of a sub n is not zero. Harmonic, which is, as we know, divergent, and the p series when p is greater than 1, they're convergent. The geometric series, remember the two definitions for the nth partial sum and for the sum. The integral test, the comparison, the limit and direct and limit, alternating series, and also absolute convergence, and the ratio and the root tests. So let's look at a few examples from page 781 and see how we analyze those. And let's start with number 9 on page 781. And we have the sum and the series of n squared minus 1 over n cubed plus 1. So because of these terms, I would think of comparing it with the limit comparison test from n equals 1 to infinity over 1 over n, which is the harmonic series, which is divergent. So let's look at the limit of a sub n over b sub n as n approaches infinity. Here is a sub n, and of course this is b sub n. And let's see how we simplify this. Okay, so this will be limit as n approaches infinity from n squared minus 1 over n cubed plus 1, and this is 1 over n, so I will flip into n over 1. So this limit, n approaches infinity, n cubed minus n divided by n cubed plus 1. We know either L'Hopital's rule or factor out, and we get the answer to be 1. Remember, as long as this is a constant, it exists and it's greater than 0, then we know since b sub n, this series is divergent, so will this be. Okay, so therefore, by the limit comparison test, n squared minus 1 over n cubed plus 1 is also divergent. Good. Let's look at a few more. Okay, let's look at 13 on the same page, 781. And we have the series of e to the n over n squared from n equals 1 to infinity. So obviously, we should always have the test for divergence in mind. So when we look at the limit as n approaches infinity from a sub n, which is this, e to the n over n squared, and when we differentiate, because this is an infinity over infinity, this answer will always be, the numerator will always be bigger than the denominator. So this is divergent by the test for divergence. Okay, that was 13. Moving on to 19. And we have the series 1 over n cubed plus 1 over 3 to the nth power. Remember, one of the properties of the summation notation, or the series if you want, is we can rewrite it as a sum of two series. Well, we know that this is convergent because it's a p series with p equals 3. We know that this is convergent because it's a geometric series with the common ratio 1 over 3, which is less than 1, of course in absolute value. So this sum of two convergent series is also convergent. That was 19. Let's take a look at next one, 21. on 781. And we have the series from 1 to infinity, 3 to the n squared, n factorial. This is a typical situation for a ratio test. So let's look at the limit as n approaches infinity. Again, the absolute value is redundant. Everything is positive, but still. 3 to n plus first, n plus 1 squared over n plus 1 factorial times, and we flip it because we are dividing them. 3 to the n power and n squared. And let's see what goes away from here. Let's move on to page 3. So limit n approaches infinity. 3 to the n plus 1 over 3 divided by 3 to the n is just 3. Then I'm going to write n plus 1 squared over n squared because this limit will be 1. Then we have n factorial, and the denominator is n plus 1 times n factorial. So this has degree 3, this has degree 2, so the limit is 0, is less than 1. So then we conclude that the original series, which was 3 to the n squared over n factorial, is absolutely convergent by the ratio test. Okay, that was 21. Okay, let's look at 35 on the same page. N factorial over e to m squared, n equals 1 to infinity. Okay, same type of problem. We have the limit as n approaches infinity. So n plus 1 factorial over e to n plus 1 squared times e to n squared over n factorial. And let's see what we get in this case. Limit as n approaches infinity. This is again n plus 1 times n factorial over n factorial. Here we have e to n squared minus, when we square this, careful, I didn't write it clearly here. Let me make sure that this is super clear. Okay, so n squared minus 2n minus 1. So this is limit as n approaches infinity. The numerator has an n plus 1, and the denominator has e. All these are negative, so now 2n plus 1. As at infinity, obviously this will be much smaller than this, so the answer is 0, which is less than 1. Therefore, from here we conclude that the original series, which was n factorial e to n squared, is absolutely convergent by ratio test. And this was 35. Okay, let's see, is there anything else? Anything else here? Yeah, so let's also look at 41. On page 781. And this is k equals 1 to infinity, 5 to k, 3 to k, 4 to k. So let's take a look at the limit of a sub n, which is this. Okay. Sorry, k. Okay, so limit as k approaches infinity. If we factor out in the denominator 4 to k, then 3 over 4 to k plus 1. This at infinity, because the denominator is bigger than the numerator, this will approach 0. So this is 1. So this whole thing will be 1. Now 5 over 4, because the numerator is bigger, the answer will be infinity. So since it's not 0, but the test of convergence, so divergent by the test for divergence, because it's not 0. Thank you.